Welcome to this explainer. Okay, today we are completely demystifying authentication. If you've ever felt totally lost staring at a massive wall of network logs, you are definitely in the right place. By the end of this session, you're going to be able to confidently debug access failures. And the best part is, you'll do it without needing any sort of background in cybersecurity. Let's dive right in.
Look, we've all seen this exact frantic support ticket, right? A user is completely blocked, the pressure is on, and the developer's response is just a super cryptic, "Hey, check the token." It is a totally frustrating loop. But today, we're skipping that frustration completely. We're going to learn exactly what that token is, how it gets there, and precisely what you need to look for when things go off the rails.
We're starting right in the trenches. You pull up the browser's network tab, and boom. That dreaded 401 unauthorized error is just glaring back at you in bright red text. It's telling us something is broken, sure, but it is definitely not telling us why. To figure that out, we really need to know how this whole thing is actually supposed to work.
So let's map out the standard four-step OAuth 2.0 authorization code flow. First, the user authenticates with an authorization server. Think logging in with Google or GitHub. Second, the app asks for authorization. Third, if the user says yes, the server fires back a temporary single-use authorization code. And finally, in step 4, the app's backend secretly swaps that temporary code for the actual access token. That token is basically the golden ticket the app needs to access data.
And that exact access token the developer told you to check? Well, it's usually a JSON Web Token, or JWT for short. Out in the wild, it just looks like a massive string of URL-safe gibberish. But when you paste that exact string into a debugger like JWT.io, absolute magic happens. It decodes the whole thing and lights it up in 3 distinct colors.
So, what are we actually looking at here? A signed JWT always has 3 parts, separated by little dots. That red part, that's the header. It literally just tells us the token type and the cryptographic algorithm used to sign it, something like HMAC or RSA. Then there's the purple part, the payload. This is the real meat of it, the claims, which are just statements about the user and the token itself, like their ID. And lastly, the blue part is the signature. That's the cryptographic proof, mixing the header, payload, and a secret key to guarantee absolutely nothing was tampered with in transit.
Now, zooming into that purple payload section, there are a bunch of claims. But for us, one absolutely reigns supreme, the exp claim. It stands for expiration time, and it's a Unix timestamp that dictates the absolute exact second that token dies and becomes invalid. Honestly, the vast majority of all failures you're going to investigate come down to this single tiny piece of data just being stuck in the past.
Section 1, the usual suspects. Let's look at the 5 most common auth errors support engineers actually encounter in the wild.
Suspects 1 and 2 get confused all the time, but just keep this super simple door analogy in mind. A 401 unauthorized error means your token is missing, malformed, or just plain expired. Basically, you need a key to get in. But a 403 forbidden error? That means authentication actually worked. You have a valid key, but you simply don't have the right permissions or scopes in OAuth speak to open that specific door. Like maybe you have the read scope, but you're trying to delete something. That is a classic 403.
Our third suspect pops up right during the initial handshake, the infamous redirect URI mismatch. After logging in, the server tries to redirect the user back to the app. But listen to this. For strict security reasons, the server demands an absolute character-for-character match with the web address the developer originally registered. It doesn't mean mostly match, I'm talking exactly. Even a single missing trailing slash, a weird port number, or using HTTP instead of HTTPS will trigger a complete failure.
Moving on to suspect number 4, the invalid_client error. Remember step 4 of that OAuth flow we talked about, where the backend swaps the code for the token? Well, to pull that off, the backend actually has to prove its own identity using a client ID and a client secret. If you see this error, it just means the application is using the wrong ID or secret password to authenticate itself to the server. Usually, it's just a simple configuration typo or maybe an expired secret key.
And finally, suspect 5 involves PKCE, which is actually pronounced Pixie, believe it or not. It's an OAuth extension used to stop interception attacks, especially on mobile or single-page apps. It works like this. The app sends a hashed code challenge right in step 1. Then, in the final token exchange, it has to send the raw, unhashed code verifier. If the server hashes that verifier and it doesn't perfectly match the original challenge, bam, you get an invalid_grant error.
It essentially means the app lost the verifier, or someone's actively trying to hijack the flow. Okay, let's bring all of this theory together with a real-world investigation. Imagine this. A user submits a very angry ticket saying they get kicked out of the app and forced to log back in exactly every 30 minutes. They're frustrated and they want answers right now. So, how do we apply what we just learned?
Well, we don't guess, we inspect. We pull up our tools, open the browser's network tab while the user reproduces the issue, and we grab that failing authorization header from the exact API request returning the 401 error. Next, we paste that bearer token string straight into our JWT debugger. We hone in on the purple payload, specifically that EXP claim, and convert the Unix timestamp. Boom! We immediately see the timestamp is way deep in the past. The token is officially expired.
Now here's the catch. An access token expiring every 30 minutes? That's actually a totally normal security practice. Tokens should be short-lived, but the user should never even notice. The app is supposed to use a long-lived refresh token in the background to quietly go get a new access token before the old one dies. Since the user is actually getting kicked out, checking those network logs reveals our true culprit. That silent background process to rotate the refresh token has completely failed.
Just look at the difference in the support ticket now. By doing this quick, simple check with the Network tab and a JWT debugger, you've transformed a vague, totally unhelpful complaint into a laser-focused, actionable diagnosis. You aren't just passing along a headache, you're handing the developers the exact location of the fire. They don't have to waste time guessing if it's a scope issue, a mismatch, or a bad secret. They know exactly what to fix immediately.
And I'm going to leave you with this final, somewhat terrifying thought. Throughout this whole explainer, we just proved that literally anyone can copy a token from their browser, paste it right into a public website, and read the entire payload in plain text. Decoding a JWT doesn't require a password, it doesn't need a decryption key, it is just base64 encoded. So you really have to ask yourself, and maybe your dev team, what secrets, personal data, or sensitive internal system details might your APIs be accidentally exposing in plain sight right now?